think more about the cross-cutting concepts, and you'll get there. But these are the important features of models. So model building, as in art, so in science, when you build a model, you have to decide what to focus on and what to leave out, what to represent in detail, and what do you need to look at more carefully in order to be able to represent it. You have to decide what to foreground, what to leave out, and you have to decide how to revise and refine. So building a model, like painting a picture, it's a process. It's not a one-time thing that you do it and it's right or it's wrong. It's a process where whatever model you start with can be refined and developed. And this is also, and same is true when you make a design in engineering, the idea that there's not just one right answer. That there's a process by which you get closer and closer to the right answer. But you're not wrong because you started with a different model from somebody else. You have a model now, how much of it, what part of it works, what part of it doesn't, and how do you need to refine it to make it better? You have a design, but it falls over. What do you need to do to refine it to make it better? This idea of fail forward, the idea that you try and revise and then you get there and you learn that way, is a very important message about learning for kids. It's not, oh, I could or oh, I couldn't. And it's not that those people can do it and I can't. It's that whatever we start with, we can work towards solutions. And that encouraging children to start from where they start and work to where they need to be is a very important message about learning. Okay, so here's an example of a classroom that had been working to develop models for a gas. These are, I think, 6th graders, somewhere in middle school range at least, and so maybe 6th or 7th. They've done a whole lot of different phenomena, and now they're asked to explain one. The teacher says, look, I opened this jar at the front of the room, and it contains something smelly. And I asked the students to raise their hands when they could smell it. And the students in the front of the room raised their hands, and then gradually it moved till the students in the back of the room had their hands up. Now explain, how did the smell get from here to the back of the room? Develop a model that can explain it. And here, this is actually student work. One kid, at least, but actually 75% of the students had the idea that air was made of particles, and 25% of them still had something else in the air as well as the particles, so they had the particles there. It's one of the things when you teach, you just teach, air is made of particles and they collide with one another. Well, the student thinks that there's got to be something between the particles holding them up and holding them apart, and so they invent wind. That's what's in the room to hold up the air, or whatever they might have in their model. So this is a student who's now got it, right? They've got the air molecules and the ammonia molecules. We don't care that they don't know what air is made of. They just know that the ammonia, which is the smelly stuff, is something different. And they have arrows that say the particles move in straight lines until they bump into something and then they go in another direction. And here they have a very sophisticated model of what's going on in the air. And if you ask most students who've been taught what air is to do this, they cannot do it. So the process of doing the modeling in the classroom has reached the point where on a test they can do the modeling. And it tells you up there what happened when the students were doing this. This is the kind of result we're wanting. Working through a series of experiments which ask you to think about how air causes pressure, about what's going on in the air in various situations, to be able to answer a question like this on a test. It's a very different question than asking the question, what is air made of? Right? So this is the kind of work we're looking for. This is coming from a curriculum that was developed in Michigan, a middle school curriculum. So that's one example of a curriculum. It was developed before Next Generation Science Standards, but one of the developers who developed it was on the framework committee, and another one was on the writing team, both for the framework and for the standards. So there's a big overlap between the development of this curriculum and the ideas in the framework about how you should learn science. Okay, enough on practices. Do you want to stop and ask questions about practices, or do you want to go on and ask questions at the end? I probably will talk too long if we keep going. only have 10 minutes left? Wow. Well, I'm going to have to run. But one question.
No, I was just going to say that as a high school teacher, I know that I'm going to have to go back and do some of the middle school standards or try and get them caught up because they're not used to being doing this.
That's right, and that means you're going to have to keep revising your lessons for many years as kids come through that have had more and more years of this. I heard third grade teachers in a district where they've been working for a couple of years say, it's amazing. The kids come in and they say, I observe this and my claim is that. Well, your kids don't in a high school doing that today, right? So yes, it's going to take a while. As we start doing this, the kids are going to become more and more accustomed to the particular language we've chosen to describe things here, and more ready to jump in and do this kind of work. But for a while, it's going to be a struggle because you won't have kids who come through. You're in 9th grade. The kids have not had 8 years of working this way.
When will the 5th grade CST test go away?
What they're saying right now is 2017, I think, is the official number. It probably, but forget it, folks. It doesn't count for anything right now, right? So don't worry about it. Worry about what your students should be learning. And there will be new tests. What grades they'll be at, what they'll include, that's all still in a state of flux and being decided. But I can guarantee you it will be different. Okay, let's talk a few minutes about cross-cutting concepts. I see these as tools for thinking. Students cannot make connections unless they have been supported to make connections. So the cross-cutting concepts are what connects physics, chemistry, biology, or science across the disciplines. Right, here's the list. Patterns. Looking for patterns, that's everywhere. And in each case, after the concept, I've written a question. Because what these concepts become are tools for students to do the questioning they need to do to be able to independently solve problems. So if I'm looking at a phenomenon I've never looked at before, it's useful to ask, what patterns am I seeing? And what do I need to do to explain those patterns? Right? How can I explain what caused what I'm observing? Right? Scale, proportion, and quantity. On what scale do I need to measure? What proportional relations? What units of measure? These are questions that the students should be asking as they're thinking about a problem. And by the way, folks, when you use math in science, it looks very different from the way it's been taught in math. Although the new math standards are moving in the right direction, it's still a struggle. Think about this. When you ask students to think about density or speed, they're taking a ratio, but it's a ratio of incommensurate things. Distance is different from time. Taking a ratio of distance over time is not like taking a ratio of 3/5. Right? It invents an entirely new idea. Distance over time is speed. Mass over volume is density. Density is not the same as mass or volume. Speed is not the same as distance or time. So actually looking at the units and thinking about what the units are telling you, what it means to take ratios of incommensurate quantities, that needs some talking about the first time students need it. That needs support to transition from ratios as ratios of fractions of a pi and ratios as they appear in science equations that have units in them. So the whole idea of units, which physics teachers teach you, ought to be being taught in 4th, 5th, and 6th grade, where we're meeting things like density and speed for the first time. So thinking about how you bring the math that they do understand, fractions and ratios, by the time they're in 4th grade. But how do they use that in a science context? Well, that's a new concept. That's not the same thing as what they've learned in math. And so getting to the point where the equations with units of measure in them and different kinds of units of measure. Right? Yes, I can convert from inches to meters, but I cannot convert from inches to seconds. Right? Those are entirely different kinds of units. And so thinking about what's going on there and supporting students to understand it. Okay, well, that's the systems question. Systems are very important. You can't model unless you've decided what system you're modeling. The whole idea of systems thinking is core to the way we do science and the way we do engineering. So the question is, what's the system I'm studying, and how do I explain it? What are its components? How do the components interact with one another? What's the boundary? What's flowing in or out? These are critical questions that apply no matter what problem you're looking at. So having a set of questions that are universal is really valuable. Energy and matter, flows, cycles, and conservation. We talk about energy today, 2 minutes. I'll just do this one and then we'll stop. And the rest of it we'll have to leave for another time, or for your questions. When we talk about energy in physics, chemistry, biology, and earth science today, the poor student has no way of connecting what we're saying in physics and what we're saying in chemistry and what we're saying in biology and what we're saying in earth science unless we work to make those bridges evident and obvious and connected. So when you talk about energy in biology, you have to think, am I saying this in a way that connects to the way I talk about energy in chemistry? And the way so the energy is not in the food. The food is a resource for a chemical reaction between the food and oxygen, which releases energy, right? And that's the way it has to be taught. Saying that the food is energy is, the food is the energy resource, which is the limiting resource for obtaining energy when you live in an oxygen-rich environment. Take away the oxygen and the food won't do you any good at all. So understanding that is an important way of making the bridge. So now we've been talking about chemistry and the chemical process. How do we connect energy in chemistry to kinetic energy and potential energy in physics? We have to build the bridges so that the cross-cutting concept is truly cross-cutting. And I'll quit there. I can go on. That's the slide for what I just said. But there is so much work to do to make science make sense and be usable in the way kids learn it, rather than just as something that they really don't believe has anything to do with the world they live in. It's just something they have to learn to get through school. That's the transition we want to make. And it's critical because the more we make that transition, the more students will cross the bridge into science-rich and science-based ways of looking at the world. And that's what we need, to have the citizens are in ready, to have the workers, to have the options for our kids to move to the future. And that's why I'm so passionate about this, that I spend my retirement talking about it. Thank you.